Stanford University.
Sight unseen. We don't know how much is in it.
Yeah,
Maybe from previous class.
Yeah, it could be.
yeah, it could be. I mean, I'm sure there's an explanation.
Pit with 2 T's?
Yeah?
I found it.
You can,
Very interesting. What else did you find?
oh, look, I'm on. So why don't we get started here? I'm pleased to welcome all of you and welcome Barbara Liskov, who's here today to talk with us. It doesn't quite made the newspaper the way Barack Obama showing up at Facebook today did, but for us, it's a big event nonetheless. Barbara has been a prominent computer scientist at MIT. She's won a number of awards, including the IEEE von Neumann Award, ACM Turing Award, which I guess together constitute our version of the Nobel Prize. She has a long list of successful students, the sort of thing that all of us in academia are proud of. And I wrote a little bit about her in my book, so I've always been fond of the things about programming languages that I learned at MIT. So without further ado, though, let me welcome Barbara.
Thanks very much. So it's a great honor to get the Turing Award, but of course it comes with this downside, namely you have to come up with a talk. So in preparation for this talk, one of the things that I did was I went back and started to look at what I was doing when I did the work that led to getting the award. And I read a lot of the old papers and thought about the ideas, and it was really very interesting, and in the end I decided that that was what I would talk about. So what I'm going to do is tell you about where the ideas came from and what it led to. So I'm going to talk about this big thing of inventing abstract data types, which was really the reason that I got the Turing Award, and then the work that I did on the CLUE programming language, which was what I did to really understand what that idea was all about. I'll talk a little bit about some work I did on type hierarchy, and then I'll conclude. So what happened was I got my PhD at Stanford in 1968. I actually did my PhD on chess endgames, working with John McCarthy. I knew that partway through my graduate career that I wanted to get out of AI and into computer systems. This was because I felt that AI was too hard. I felt like I just couldn't make progress on the problems that I wanted to work on, but I was very interested in the area of systems. And I decided not to try and do that while I was a graduate student, because it seemed that the best idea was to finish up a PhD and get out so I could get on with my career. And I felt that switching areas midstream would have been non-productive. So I finished up my thesis in AI, and then I went to work at the MITRE Corporation. And the MITRE Corporation is located in the Boston area. Part of the reason why I went back there was because by then I had met the man I was going to marry, and he was located in Boston, so I wanted to get back to the Boston area. And MITRE it's a nonprofit organization that does work on government contracts. And so I went to MITRE and I was handed a project. They had a grant from the government to work on what's called microprogramming. So microprogramming was a hot topic in those days. And what microprogramming is it's a very simple machine, effectively a RISC architecture. And the idea was that you would get that machine, but nobody would want to actually write programs in that machine. So my project was to take that machine and come up with a different architecture that had more standard instructions, more like what people were using to write programs in those days. And that was the days of the 704, 7094, and so forth. And so that was what this first project was in the Venus machine. It used this micro-programmable computer, the Iterator 3. My recollection is that the Iterator 3 had 16 instructions. I think it had 16K of read-only memory. So the idea was that I would program that read-only memory to provide the instructions that were more like a conventional instruction set. It had a paper tape reader. that was sort of it. So it was a very, and 16K of regular memory. So it was a very small machine. And I hadn't been studying machine architecture, so this was a great first project for me to get my feet wet in moving into the systems area. And so I did this project in the Iterator. I came up with an instruction set. I programmed it in the microprogram machine. And this was a pretty conventional instruction set with one exception. I put semaphores into the hardware. And the reason I did that was because I had read Dijkstra THE paper, and in fact Dijkstra even came to MITRE while I was there, and I talked to him about the THE system and semaphores, and I thought they were a really nifty idea and would be very useful to have directly supported in the hardware, so I put them in as 2 of the instructions that were supported by this machine. So I finished the Venus machine, and then the obvious question was, is this good for anything? So the second part of the project was to try and prove that it was good for anything. And so to do that, I designed and implemented the Venus operating system. So you can see I'm really, getting into systems here. And the Venus operating system was a good vehicle for this because it was a small multi-programming machine. So it was able to take advantage of the semaphores because there was going to be concurrency inside the machine. And also at this time, this is around 1969, 1970, operating systems were in their infancy. So that was a very interesting research area. At that point, the abstractions that we come to know today were still in the process of being invented. And so I was really doing research in operating systems at the same time that I was exploring whether I could use this machine for something useful. So I designed and implemented the Venus operating system. It supported 16 concurrent users, had multiple processes, had a little scheduler, had files, had virtual memory. It had all the stuff that we seem to think about, being in an operating system. Okay, so now I finished the project on the Venus operating system, and I'm at MITRE, and I'm still a pretty junior researcher. So what happened was I was handed another project. So somebody said, do this work on program methodology. What they really said was the government has gotten very concerned about the software crisis. So this was like the beginning of the software crisis. And the government had noticed that our ambitions were far outstripping our ability to write software. And so they had asked MITRE to look into the question of, isn't there a better way to develop software where you have a better chance of ending up with a program that actually does what you're supposed to do? And of course, really, there is still a software crisis. But it was really severe in those days. And in fact, if you look at the history of software over the years through the 70s and the 80s, you just see this failed project after failed project. Millions of dollars were spent, millions of lines of code were written, and in the end, you had to scrap the entire thing because it didn't do what you were supposed to do. And so people were really struggling at this point to try and understand what methods we could come up with that would help us to control the development of software. So this is what I was working on in this project. And what I did, of course, was I went out and I read the literature. So here's an area I didn't know anything about. And so I started reading all the literature, and I'm going to tell you about some of the papers, which were excellent papers, and I recommend them to people today. I feel that one of the problems in our education in computer science is that we don't tell our students enough about the past. I discovered that my students knew almost nothing about my graduate students knew almost nothing about the past. And I think it's really good to include some of these papers in our curriculum so people can see where we're coming from. First, though, I wanted to mention that program methodology is really about 2 related but different topics. One of them has to do with the design process itself. So this is one of the things people were talking about. How do you design programs so that they end up doing what they're supposed to do? But the other one has to do with the program structure in the abstract. How do you structure programs so that in the end you can reason about what they're doing? And I read papers on both topics. So the first paper I want to tell you about is this very famous paper by Dijkstra on Goto Statement considered harmful. And this wasn't actually a paper. It was a letter to the editors of the communications. It was only a couple pages long. And it was extremely controversial at the time, which is hard for people to understand today, because today, if you think about the languages we're using, they don't have Goto statements in them. Goto has long, given up the ghost and is no longer considered a necessary part of writing software programs. But at the time that Dijkstra proposed this, people were writing in languages like Fortran. Gotos were a very important part of those programming languages. And the reason why this was such a controversial paper, I think, was partly people were offended. They would say, I write programs with Gotos, and these are perfectly good programs. And Dijkstra was kind of saying programs with Gotos are bad. In truth, you can write good programs in any terrible programming language, and people could use Gotos in a very well-disciplined way, and that would be okay. And then it was also, it's not what I'm used to. And there was also a concern, I think, that they might not be able to build the programs they needed to build. So programming languages in those days were not like they are today. If you have a language that doesn't have an exception mechanism, for example, then Gotos are a very good way to handle exceptions. You can pass a label as an argument to a routine. It can branch to that label to signal an exception. You get it out of the main flow of the program. If your language doesn't support exception handling, then what do you do? Or, for example, if you don't have a case statement, you can use an array of labels to simulate a case statement. It's a valuable structure. So the control structures in the programming languages weren't that great also, so people were worried about that. Now, what Dijkstra said in this paper is he said what seems very obvious today. Programs are complicated, and it's not easy to reason about what they do. And when you reason about the correctness of a program, you look at the program text, which is a static thing. But what you're reasoning about is the execution of the program, which is a dynamic thing. And his argument was, we would like to keep the two things as close together as possible. So the static ought to be very close to the dynamic. And if you have a program with branches all over the place, and people used to talk about bowls of spaghetti, because people really did write programs where they branched all over the place, then it can be arbitrarily difficult to relate the static description to the dynamic behavior. And he made an analogy to the debugging process. He said, supposing you're debugging your program, you have an error in it, you're at a particular point in the control flow, and you want to figure out what went wrong. Well, if you're using a programming language or a program that doesn't have Gotos in it, it's relatively easy to figure out how you got to where you are. And this is what you need to understand in order to figure out what went wrong. If you have a program with Gotos, it can be arbitrarily difficult to do this. So this was a very influential paper, and as you said, you can see that Dijkstra ultimately won the day because the Goto has disappeared from our programming languages. Here's another very important and influential paper by Nicholas Weert, and this one is on a different topic. Dijkstra's is about the structure of programs. This one is about the design process. And this is one of the early papers that advocated top-down design. So what Weert said in this paper was, the way you design a program is you start with the problem statement, and you think about an abstract program at a very high level that accomplishes what you're trying to accomplish. And after you're satisfied that that abstract statement, which he thought of as being written just as a sequence of comments, after you're confident that that program does what you're supposed to do, then you select one or more of those statements and you iterate that process. And his example was the 8 queens problem. So he said, well, the way I'm going to think about the 8 queen problem, I'm going to make a single design decision to get started, and his decision was to work on the problem column by column. So the basic core of the solution is, you imagine you have a solution to the 8 queens problem that takes care of the first n columns. So it satisfies the condition that there are no queens in any of the ways that they can attack each other. And then you try to add one row, one column to the solution, and try to find a position for the queen on that column. And if you can find one, that's fine, you'll go on to the next column. If you can't, you backtrack and try again. So that was his basic solution, and he wrote a little program like that, and then he refined it to end up with the final solution. Now, we know today that top-down is not the whole solution, because you have to design programs through an iterative process where as you get lower down, you discover that things weren't quite right, you have to back up and try again. But nevertheless, he was absolutely on the right track. Because if you don't have a fundamentally top-down process, then how can you possibly expect to have a program that does what you want it to do? You have to start firmly with the project in mind, the problem in mind, and then you can work fundamentally top-down, although you may have to go up and down a bit when you're working out the design. Here's another very important and influential paper. This one's by Dave Parnas. Dave actually wrote 2 papers at about the same time. Both of these have more to do about program structure than they have to do about program design. And what Dave is saying in this paper is that modularity is what matters. And modularity is absolutely what matters in program in building programs that actually work. What you really want is you want to divide your program up into modules. These modules have hidden insides. They're encapsulated. They're black boxes. They have interfaces that are used to communicate with the rest of the program. And the power of modularity is that if you do it right, you can reason about a huge program module by module. You can think about each module in isolation. You don't have to reason about 1,000,000 lines of code at once. You can think about 1,000 lines at a time. But in order for this to work, you have to understand what modules are, and in particular, you have to have interfaces that sort of capture what's going on. And so that's what Dave was talking about in this paper, and he was saying that in order to understand modularity, you have to understand how a module is connected to the entire rest of the program. And in this famous statement, the connections between modules are the assumptions which the modules make about each other. What he's saying is it's not just that one module might call another. There might be all sorts of other connections. They might share files. They might share global variables and so forth. And you have to understand all these connections in order to have an interface that allows you to separate the reasoning and do modular reasoning. OK, so I read those papers. I read a bunch of others. And as I said, I was surprised when I went back at how lucid and understandable these papers are. They're really good papers. And I realized as I was reading them that I had actually myself invented a program methodology, because I had been working on the Venus operating system. This was a big program. And I knew going in that it was going to be hard to get that program to work. And so I developed a design methodology really without thinking of it, just as a way of sort of keeping the complexity under control. And what this design methodology consisted of was what I referred to as partitions. So the way the programs were written in those days, and in a way Algo 60 was responsible for this, or was mirroring this idea, is there was a bunch of global state, and then there might be inner blocks, but programs communicated through that global state. And a lot of the trouble people got into was these were the connections Parnas was talking about that caused so much trouble. What I did in Venus, as I said, there is no global state. Instead, what there is we're going to divide the global state up into these partitions. Each piece of global state is owned by a module. That module completely controls what's going on inside, and it provides an interface to the outside that wasn't just a procedure, it was a bunch of operations. So, as I said, I sort of realized I had this when I was reading these other papers, because I hadn't really thought about it as a methodology when I was working on the Venus system. So I wrote this up, and it was presented at one of the IFIP congresses. Now, by now, we're in 1971 or so, and I've been doing this work on program methodology. And one of the things that I did during that time was I wrote up a paper on the Venus operating system, and I submitted it to SOSP, which is the top systems conference, and it became a prize. It was one of the prize papers. And Jerry Saltzer, who is a well-known person in the systems area and a professor at MIT, was the person who ran my session. And as a result, I was invited to apply to MIT. And so I did, and I decided to go to MIT. So that was serendipity based on the Venus. And actually, so I left right when I was finishing up this work and writing this paper on the partition. I moved from MITRE to MIT. Actually, it was a really good time to move, because what had happened was when I got into program methodology, I really found my field, because I was fascinated by that topic. I thought it was so important. It was so puzzling. It was just really an interesting problem to work on, and I would not have been happy anymore at MITRE, being handed the next project that the government had its eye on. I really wanted to focus on this. So one of the wonderful things about being a faculty member is you do get to choose your problems. It's true you might have to persuade someone to fund them, but it's both the strength, and the weakness of being a faculty member. You have to find those problems, but when you have those problems, you can really, pursue them. So I went to MIT in the fall of 1972, and I was absolutely focused on this problem. I felt that there were a number of really good papers out there, and I'm thinking here particularly of the papers of Dave Parnas and his ideas about modularity, and also my own ideas about partitions. I felt, though, that in these papers, they were always presented in the context of an example. And so they would say, here's this great idea about how to organize your program. Here's how you build these modules in this particular example. And it all seemed very convincing until you tried to apply the ideas to a different problem. And then it was totally unclear what to do. And so I felt, well, if we're going to make progress in the methodology area, we have to have a way of going from these papers to some idea that people can really understand. And so that's the problem I was focused on in the fall of 1972 when I went to MIT. And sometime in the middle of that fall, I can't remember when, I had one of those wonderful aha moments that very few of us are actually lucky enough to have, where all of a sudden I saw that you could connect these modules, my multi-operation modules, to abstract data types. And today, I mean, it all seems obvious, you know, but what I had in mind was the module was in fact the object. The operations were the operations you used to interact with the object. Inside was the representation of the object and all the complex program that had to be carried out in order to run the operations. And that was the connection. And looking back, so the question is, you know, where did this idea come from? And looking back, well, I can't tell you, you know, except I can tell you some things, and this is partly really for the students in the audience. One thing I can tell you is that the idea was waiting to be discovered. Because when I looked back at these papers, I saw abstract data types all over the place. It's just that nobody had sort of made that connection then, but you could see it floating around in those papers when people talked about these examples and they talked about their modules and so forth. There the idea was sitting. Another thing was that it wasn't discovered only by me. There was Bill Wolfe's group at Carnegie Mellon, and other people got similar ideas about the same time. And this is very common. When an idea is ready to be discovered, it's typically discovered by more than one person. The third thing, though, is, and this is for the students, is I was really working on this problem. I mean, I was thinking about it all the time. I have never been a person who believes in working all the time. I've always worked a pretty regular, you know, 9 to 5. What actually happened was I went to work before I went to graduate school, and I discovered the joys of a regular life. And so when I went to graduate school, I decided, you know, none of this business of letting the work go, and then on Sunday I have to spend all day worrying about how to do the assignment that's due the next day. I'm just going to go to work every day, you know, do my work, not get behind, and then I can go home at night and do something else. And I've sort of continued that with my career. And one of the things I get out of this is this wonderful downtime, which is extremely productive. So I think, you know, if you work too long, you get to a point where you're so tired you're not making progress anyway. And if you stop working, of course your subconscious doesn't stop, you know, and that time when you're not thinking is actually extremely productive. And I've often had the experience that driving in to work in the morning, when I'm kind of reviewing what would I work on today, I discovered that some problem I didn't know how to solve the day before, now I understand, you know, here's a way to approach that problem. So anyway, I was really working hard on this problem. You never make progress if you're not working hard. So I was obsessed with this problem. Even though I wasn't working on it all the time, it was always in my mind, and that led to my being able to make this breakthrough. Okay, so I already said that. All right. So I was thinking about this in the fall, and then in the spring there was this very influential meeting in Savannah. And notice this is a joint SIGPLAN SIGOPS interface meeting. So SIGPLAN is the programming languages group, SIGOPS is the operating systems group, and this meeting was ostensibly to talk about programming languages in which to build operating systems. That was a kind of a hot topic at the time. Not a very interesting topic if you think about it. I mean, programming, because, you know, there's a small number of operating systems, there's a vast sea of applications. You know, programming languages are really for applications. Operating systems are just a small piece of the pie. But in truth, that's not what people were talking about at this meeting. They were talking about programming methodology. And I presented my ideas about abstract data types. And Steve Zillis, who was a graduate student at MIT, had written a little paper for that meeting that had some similar ideas in it. And so Steve and I started to work together. And what we were working on now was we had this idea about abstract data types. What did it really mean? So how do you flesh it out? And Steve was a really good person to work with on this because he was not your normal graduate student. He was in his 30s. He worked for IBM. He'd been working there for many years. He knew lots and lots about the programming languages of the day. You know, IBM was a big player in those days. There was Fortran, there was COBOL, there was PL1. And then, of course, I came out of AI, so I had the Lisp background, and between us, we pretty much covered the waterfront with respect to the programming languages that existed those days. And Steve had already been doing some programming language work, so that was good because we were really moving into the programming language arena, since the whole idea was that this idea of modularity was very abstract, but by mapping it to abstract data types, I was moving it into a domain. This is why I was so excited about it, that matched what programmers were already doing. Programmers already understood about data types. You know, they had arrays, they had lists, they understood that you didn't muck with the representation, that was hidden underneath. You just called the operations, that's how you interacted with it. So going from there to the idea that you could invent your own, I mean, that was really right in the programmer domain, and so that's why I thought it was going to be so useful. Okay, so Steve and I did what you do. Right? We read the literature, and I'm going to tell you a little bit of the literature in the programming language arena that we looked at the time. And the first one is this paper by Steve Schumann and Pierre Girand on extensible languages. And this was a hot topic at the time. Okay, so what's going on with extensible languages was that people were worried in those days about whether there was such a thing as a practical universal language. Okay? Now, today we know that there are practical universal languages because we use them all the time. C is a universal language, Java is a universal language. I mean, most of the languages we use are universal languages. You can use them to implement anything. But people at the time were not confident that these higher level languages that people were introducing would necessarily be good enough to do the job. And the reason they worried about that was because there is a loss of power as you move up the stack, so to speak. Okay, because when you're in machine language, you have all those lovely little machine instructions, and you can do anything with machine instructions. But when you go up to a higher level language, you don't get to use those machine instructions any longer. You have to use the constructs in the language, and the worry was that in making that jump, you lost something important. And so the work in extensible languages was sort of motivated by this worry. And what they pointed out in this paper was that there was research in two different topics in this extensible language domain. The first was what they referred to as syntactic extensions. And there the idea was that you could actually change the syntax of the programming language. This is a kind of an idea that sucks you in at first. So, you know, the good example is I have to use factorial all the time. Why can't I use the factorial symbol when I want to use factorial rather than having to use that awkward functional notation? But in reality, when you start to think about it, it's a really bad idea. And the reason it's a really bad idea is because, as we know today, but people did not understand then, it's reading programs that matters, not writing them. And in order to make programs readable, at the very least, you better have a syntax that somebody can understand. And so if people can start to play around with the syntax, so what you end up with is a bunch of symbols and you don't even know what they mean, this is not a very good way to start reading programs. It's okay if you take the syntax and you tailor it for a domain, and then you're talking about a domain-specific language where there's going to be a bunch of people that all work in that area. But if it's in fact just a one-of, that's not a very good idea. The other thing they talked about in that paper, though, was what they called semantic extension. And there, what they had in mind was the kind of stuff that Bob Balzer talked about in his thesis on dataless programming written in 1967. What Bob did there was he was sort of approaching the idea of an abstract data type. So, but it was limited in what he was trying to do. He sort of thought that all data types are collections. And therefore, all data types had four operations. There was an operation to put something in the collection, an operation to take it out, an operation to look it up, and an operation to modify it. And then he had some syntax to go along with this, so you could use the assignment symbol in special ways for push and pop, for example, if that was a particular kind of collection that you wanted. Now, you can see that this is a step along the way to data abstraction. The problem, of course, is data abstractions are not all collections. And even if they were, four operations is not necessarily enough operations. And then furthermore, there was no encapsulation, so it was just syntax. It sort of grouped things together. It gave you a little way of accessing them. But underneath was a representation. You could modify that, whatever you wanted to do. This is one of the early papers on Simula 67. This paper appeared in what Steve and I used to refer to as the Little Black Book. So this is a very good book to have in your library. It's a book that has 3 monographs in it. This paper by Dahl and Hoare on Simula 67. There's a paper by Dijkstra on Top-Down Design, and a paper by Tony Hoare on data structures. It was a very influential book with very interesting papers. So Simula 67 was a very interesting language. It wasn't invented for general programming methodology. It was a simulation language, but it had in it classes. Classes had multiple operations. It was a very influential language for the Smalltalk development, which went on concurrently with my work on abstract data types. and did not at the time have any encapsulation. And so Steve and I sort of decided we weren't interested in Simula because it had classes, it had inheritance, but it did not capture this notion of encapsulation that we thought was such a critical notion in this idea. This is a very interesting paper by Jim Morris. Jim Morris was a professor at Carnegie Mellon, so he was very influenced by Dave Parnas's work. Dave Parnas was at Carnegie Mellon when he wrote those papers. And here we're back to modularity. And what Jim is looking at is the question of how do we divide a program up into modules so that we can be convinced that modular reasoning is going to work. Remember, the power of modular reasoning is I only have to think about the module in isolation, and I don't have to worry about the whole rest of the program. And I can do that module by module. Each one is reasonably understandable, and then, you know, in the end, I can understand the entire collection of modules. So what Jim said in this paper was there are certain criteria that we have to obey in order for modularity to work. The first thing is that inside the module is a whole bunch of state, and it should not be the case that anything on the outside, any code on the outside, can modify that state. This is clearly very important because if you didn't have that property, then how could you reason about what's going on? You'd have to think about the whole program. The next thing he pointed out was that, in fact, it's not even okay for programs on the outside to read the state. Now, reading the state does not interfere with modularity, but it does interfere with another very important property, which is the ability to do modifications. So another virtue of modular program construction is that you can take this module, throw it away, re-implement it, maybe changing its interface a little bit or maybe just making it run better. But you can only do that if the rest of the program isn't going to be affected by the fact that you're changing what's going on inside. And then he had a third point about making up fake objects, which was a little less interesting. But the point is that this was a really very early paper that sort of captured the main things you had to understand in order to make sure that modularity worked. Then Jim went on to say, well, I don't know how to implement this, but here's a way. And basically, he came up with a kind of an encryption scheme. So he had operations to seal and unseal. So the idea is the module would produce an object. It would encrypt it on the way out. This meant that nobody on the outside would be able to get at it. And furthermore, when it got passed back in again, then you would decrypt it using the key that only this module knew. And therefore, you would either see it was in good condition, or if it had been mucked around with, you would know that things were broken. Of course, you wouldn't want to implement this with encryption. It'd be too expensive. And Jim never really said how he thought seal and unseal would be implemented, but it was sort of the basic idea. Okay, so we read these papers. Oh, here's a final paper by Bill Wolfe and Mary Shaw, also at Carnegie. So Carnegie was sort of a hotbed of this stuff at that time. Global variable considered harmful, and really I already talked about how global variables are bad, and you can see their topic comes out of Dijkstra's paper, Goto considered harmful. But they were just sort of finishing up the story about why you really did not want programs to communicate through global state. Of course they do, unfortunately. It's called the file system, and we sort of can't get rid of that, or the database. You know, it's hard. All right, so Steve and I read those papers, we read a bunch of others, and my recollection of the summer of 1973 is that it was sunny every day in Cambridge, Massachusetts, which of course is obviously not true. But Steve and I, our pattern was we would meet for lunch every day and discuss whatever we'd been thinking about since the day before. And we used to meet outside. There was a lovely courtyard outside our building, and we used to meet out there under the trees, and this is why I thought it was sunny every day, because I remember eating, you know, lunch outside in the courtyard every day during that summer. So anyway, Stephen, and then we'd separate after lunch, we'd think independently, and then we'd get back together the following day. And by the end of the summer, we'd actually come up with a pretty good formulation of what this idea of data abstraction was all about, and we wrote it up for this paper on very high-level languages. And what that paper did was it proposed abstract data types in approximately the modern form. Namely, we said a type is both a set of objects and a set of operations. And what the important thing is that only the operations are the way to interact with the objects. You can never interact with them directly. We also had a sketch of a programming language there. And so we talked about the language has to provide a mechanism for defining abstract data types, and we even had this notion of what we called clusters that had encapsulation. We wanted to support polymorphism, so it's not enough to have a set of ints. You'd like to have a generalized set. And for those of you who know the whole sad story of Java and generics and so forth, you know, polymorphism was defined in CLUE, and I'll get to that in a minute. We said at the time that we hoped that there would be static type checking, because we really bought into the idea that the more the compiler can find your errors, the better off you are. But we weren't sure you could do that, and it was polymorphism that was worrying us. We weren't sure how to get a static system that would work for that. So we said, well, if worse comes to worse, we can use Jim's seal and unseal. And then we also said it better have an exception mechanism, because those were not all that common in those days either, and I'll get to that a bit later. Okay, so now it's the fall of 1973. And what happened in September of that year is that 3 first-year graduate students showed up in my office. This is none of the glory of being a faculty member. And said they wanted to work with me on programming languages. And these were Russ Atkinson, Craig Shafford, and Alan Snyder. And the 3 of them, together with myself, were the principal designers of what came to be called the CLUE programming language. Steve, at this point, was an interested participant, but he had moved on to his PhD thesis, which was about algebraic specifications for abstract data types. And there was also a wider group that was interested in participating. Now, I went to look for photographs of people at that time, participants, and I couldn't find them. Of course, I could have tried to get in touch with them and ask for them, but one photograph I did find was this one. This is probably 1974, that's me. And this is Jack Dennis. Jack Dennis is well known to many of you. He does work in computer architecture, and Jack was a very interested participant in the CLUE programming language. Okay, so why did I decide to do a programming language? Well, in a way, it was the obvious thing to do. And we'd already, in our paper, sort of sketched a programming language, so that was a kind of obvious next step. But in fact, I had a whole rationale worked out for why to do this. And these are the reasons. Programming languages are how we communicate to programmers. Programmers think in terms of programming languages. So by having a programming language, you have a much better chance of making sure that people understand what your ideas really are. So that's the first thing. Second thing is that by putting these into a programming language with a compiler, and so people could write programs, you get to see whether the idea really works in practice. This is one of the problems with doing work in the programming languages area, is you can propose all the mechanisms you want. In the end, how do you know they really work? You can only talk about expressive power and its importance and blah, blah, blah. But this way, you know, we were going to use it to build real programs, and we were going to put it out there and let other people and see what happened. So that was very important. Another thing was, by building a programming language, we could end up with a precise definition. Okay? And that was, in fact, what I thought was wrong with many of those early papers, is that they were too hand-wavy. They didn't really explain what they meant, and this was why people were having so much trouble trying to apply the ideas to new problems. Now, mind you, in those days, the definition of a programming language was basically the compiler. Okay? So there were reference manuals. They tended to be a bit sketchy. And so, you know, somebody would develop a compiler, they would interpret the manual as best they could, making decisions, maybe not even realizing they were making decisions that weren't spelled out in the manual. And then what often happened was, when the second compiler came along, there would be a disagreement between the two compilers about the meaning of a particular construct, and an argument about this, because the compiler was in some sense the definition of the language. Nevertheless, you know, a language is a mathematical object, and we were very careful, even though we wrote an informal manual, to try and be very precise about what the meaning of everything was. And then finally, you can't ignore performance. Okay, now, I think performance is greatly overrated by people in the computer science area. Programmers tend to think that you have to get the last ounce of performance out of your program and so forth, which is absolutely not true. All you ever need is good enough performance so that your users are happy. But of course, this was brand new territory, and if the performance of the language was unbearably slow, this would also have been a killer. Okay, so I'm going to tell you a little bit about the design of CLUE at a very high level. And first I wanted to talk about the goals for the language, what we set out as our design goals. So that was the motivation. Here's the design goals. And what's particularly interesting is the design goal at the top of the slide. I don't know if Jennifer's in the audience, but Jennifer gave a talk on database programming languages basically, and she had these 4 things. Okay? Expressive power means the language has to have in it the features that are what you need in order to accomplish what you're trying to accomplish. In this case, write general purpose programs. Simplicity, since otherwise people won't understand it. Performance, good enough performance so you can build the programs you want to build. and ease of use. If it's too hard to use, people won't like to use it. And what's interesting about these goals is these are the goals for any interface design. Okay, a programming language is just a sort of a particularly complicated interface, but it's just an interface. If you build a module that you want people to use, it's got an interface, and you think about these 4 things when you design its interface. So every part of design is always affected by these goals. And I certainly have encountered these goals over and over again in the systems that I've gone on to develop. In addition, we had some very specific goals for this particular language. By minimality, we meant don't put anything into the language that wasn't sort of key to the idea of abstract data types. And by uniformity, we meant we really want polymorphism. And by safety, we meant we want as many of the errors to be discovered either by the compiler or automatically by the runtime system. Because the more errors you can get rid of automatically, the less you have to worry about for debugging. Okay, now fairly early on in the project, I added a bunch of restrictions to what we were doing. So I went into this project thinking it was going to be a concurrent language. And Jack Dennis was sitting in on my design group, and he was very interested in concurrent language. But before very long, I decided to toss out concurrency. And this was such a smart decision. I tossed it out on minimality grounds, because it really wasn't, I could develop my ideas and really work through data abstraction without having concurrency. Boy, was this a smart thing. Because if you think about the world of concurrent programming, it's a hot topic today. People have never gotten to the point where they really understand the right way to build or what the right linguistic structures ought to be for concurrent programs. I threw out Gotos because of Dijkstra's paper. I was really convinced. As I mentioned, I also didn't look into inheritance. I was really focused on the idea of data abstraction. I also made another bunch of decisions pretty early on. So having a heap-based language with garbage collection, here you can see my Lisp background. So I had a kind of love-hate relationship with Lisp, okay? But I thought garbage collection and heap-based language was great. The funny thing is, if you go back and look at the literature and programming languages of those days, people were they really objected. Pointers were evil. Of course, they were pointers, there was no strong typing, they were pointers to the stack, but nevertheless, pointers were evil, and, people were really uncertain that heaps were the way to go. By no block structure, I mean I was really thinking about building programs modularly rather than having one huge program that had an outer block and lots of inner blocks. Of course, there is block structure within the modules. I wanted that to be separately compiled, so each module could be presented to the compiler independently of the others, and you could put the program together by combining modules. But where I deviated, so this is all Lispish, if you think about it, where I deviated was in static type checking. And this came directly from my experience in doing my PhD thesis, because I found it so annoying, after I'd spent several hours trying to find a bug in my program, to see that it was an error where if I'd had a simple type checker, it would have been removed by the compiler. Okay, so I'm going to describe Clue at a very high level, just sort of showing you what the abstraction mechanisms were and describing a little bit about how they worked. So the first one is clusters, and the name Clue is the first 3 letters of clusters. That's where the name came from. Clusters were our mechanism for building abstract data types. Okay, so this is the header of a cluster. The point of this slide is to show you that we had this view that the operations really mattered. And so we picked that up in the syntax, and we have a header there that lists the operations that are available for interacting with that piece of code. Okay, here on the bottom of the slide, I'm showing you a little bit of a use of an abstract data type. And what's interesting about this part of the picture is that use of the $ notation, which is admittedly crufty. And I probably would not design it today like that. But what actually matters here is the fact that I'm combining the name of the type with the name of the operation. Okay, so this is the Clue view of the world as opposed to the object-oriented view of the world, because we thought about the operations as belonging to the type, whereas if you think about Smalltalk and all its derivatives, you think about the operations as belonging to the object. Okay, so that's the big difference, the point I'm trying to make there. Of course, there's a naming issue. That's why we had to combine the name of the type with the name of the operation, since many types would have operations with similar names. Okay, and then I'm just going to show you a little bit about what inside a cluster. We had this line rep equals. This is a type definition. And this simply stands for the instance variables. So typically the rep was a record had many components, and those together were the representation of the object. And we really thought about this object as having, in some sense, its inner representation, and then there was like a shell around it, and on the outside you could call it making, using those operations. And that was reflected in this, I'm showing you here the header of one of the procedures, because this use of the word CVT, what that's saying is as the object goes outside, it sort of grows the shell around it. You can no longer see the representation. All you can see is this abstract object that you have to interact with by calling the operations. And here think about Jim's seal. Okay, so this is like the seal operation that he proposed, except that this is all done at compile time, so there's no cost to this. It's just a point of view has changed. Okay, here's polymorphism. So that was an int set. This is a set of T. And same list of operations. The only difference is I've added a parameter. Okay, and here's an example of a use. So we thought about this as being an instantiation, what we called an instantiation, where you would provide an actual parameter to the type, giving you sort of like a specialized set, and then I'm calling an operation on that type. Okay? All right, now the problem that worried us about sets and other kinds of polymorphic types was that in general, not every actual type makes sense as a parameter for your polymorphic definition. Even sets have this problem because what you expect from a set is that the parameter type provides you with an equality operator so that you can know when an element is inserted in the set whether this is the same as some element that's there already. If it is the same, then it doesn't go in twice. If it isn't, it does, and so forth. And so this was what was worrying us. How do we make sure that when you instantiate one of these abstract types, the type you're providing as the actual satisfies what I need to rely on when I implement the type? And our solution was this where clause. So we extended the header of these polymorphic modules to state explicitly what operations were provided. Okay, so here I'm saying the only actual parameter that I'm going to allow is one that has an operation named equal that takes in 2 t's and returns a Boolean. Now you'll notice, of course, that I've picked up syntax here and not semantics. So I didn't quite get to an equality operator. I got to an operation with a name equal. But that's enough so that you could then attach to it a specification, because once you go beyond this, you're starting to talk about the meaning of programs, and that's way beyond anything a compiler can actually work out for you. Now, as soon as you have that, you can solve your problem. Because now I know when I instantiate set, the compiler can look at that type, determine whether it has the operation that's required, and either accept or refuse the instantiation. And of course, inside, I can then make use of these operations. And so here's my insert where I'm checking to see whether the type already has it. And I added a little extra stuff in this graph here, this transparency, this use of the equal operator. So we had, in clue, we had what we referred to as syntactic sugar, because you have many types that have common operations like equal, plus, and so forth, and you want to provide a convenient way for people to use them, and so here's the use of the equal operator. Okay, exception handling. So exception handling wasn't all that big in those days, and in fact, in 1975, John Goodenough wrote this paper about exception handling in which he kind of laid out the state of the art. And what he pointed out in this paper is that there were sort of two, if you looked at all the exception handler mechanisms that had been proposed, they fell into these categories. First of all, there was the termination versus the resumption model. Today, all our exception mechanisms are termination model, which means that you call some procedure, it either, if it wants to throw an exception, it terminates and just brings the exception to the attention of the caller. In those days, though, there was also a resumption model where the procedure didn't terminate, it sort of threw up the exception, something up here could do something, and then control continued in the procedure that threw the exception. PL1 had a mechanism like this. The other thing John pointed out was that there was no consensus about how you specified the handlers. So today we use call site handlers. So you associate the handler syntactically with the code of the call of the exception, the procedure that's going to throw the exception. But then people had other ideas. They said, well, maybe there's a module that all the exceptions are handled over there, and so forth. So we were determined to have an exception handler mechanism in CLUE, and the reason was that we espoused a methodology where you tried your best to make every operation be total. So we hoped, if you think about this from the point of view of specifying procedures, we were hoping to have a precondition that was always true. You can't always quite reach that, but you know, it's better to have a precondition that's true, because what this means is your code doesn't depend on your caller doing anything right. And if you can't quite make it to true, you want it to be the weakest possible precondition you can come up with. The trouble is when you try to make your procedures total, you immediately run into the case that they can't necessarily do the same thing for all operations in the input domain. And that's what's going on in this choose procedure. Choose is an operation of a set that, if given an empty set, is going to want to tell you that the set is empty, but if given a set with something in it, will arbitrarily choose some element and return it to you. Okay, now what I'm showing you here is that the syntax, okay, which is mainly interesting because you can see how much it looks like successor languages. And here's the handler. And so we had, it was the termination model, call site handlers, just like what you see today. Now, you see exception handling in modern languages, and in particular, I was thinking when I made the slide of Java versus C#, okay? And there was one place where I thought CLUE did better than either of those languages, and this has to do with the exceptions that shouldn't happen. So if you think about this from a programming language perspective, okay, so you're designing a programming language, people are going to have to use whatever rules that language has. And then think about the dilemma of the person who writes a program and in such a way that you know the exception is not supposed to happen. Like, I just checked that the set was non-empty and then I call choose. Do I have to write code to handle the empty exception? After all, the compiler doesn't know what's going on. Okay, so that's one unacceptable solution because you end up with huge amounts of useless code. Or alternatively, do I not require that that code be there, and then if for some reason the exception happens, I just start shooting it up the stack? This is an even worse solution because it means that you never know when you call a procedure what exceptions might come up from it. Okay, so our solution included, we had a third solution. We said every procedure has an extra exception, it's called the failure exception. If the procedure has an exception that's shooting up through it, so we didn't require that you write that code, but because there might be this exception shooting up through it, we generated code automatically to turn that into the failure exception. The failure exception was recognized to be special, and it meant that things were broken. Basically what would happen is it would shoot up to some high level of your program where you would go back to a checkpoint and start again, and it had within it strings and so forth that could tell you more information if you wanted. And I think this is just a really good solution to this problem that I wish had been adopted in modern languages. Okay, finally I want to tell you a little bit about iterators, and this is a kind of an interesting story. We were very worried about this program. Okay, so many data types are collections. And when you have a collection, it's because you want to do something with it. So I want to print all the elements in the set, I want to add them together, you know, whatever. Okay, so we knew we wanted to support loops of this form. And we also knew that we didn't need any special mechanism to do this because you could, in fact, program without any special mechanism, but none of the solutions you end up with were very satisfactory. So I could sort of remove the elements from the set one by one, print them. The trouble is that destroyed the set. Sometimes you wanted to use it again. So then you wrote this complicated code where you collected everything and made a new set and so forth. That's not very good. Even worse is to complicate the abstraction. So I could turn the set into an index set. Then I could talk about the first element, the second element. I didn't have to destroy the collection. But from a program methodology point of view, this is really bad because the goal when you design programs is to make your abstractions as simple as possible. And you certainly would rather not have a linguistic mechanism in there that forced you to complicate your abstractions. So with this in mind, we made a visit to CMU probably in the summer of 1975. I took my 3 graduate students and we went to CMU and visited Bill Wolfe and Mary Shaw, who were working on the Alphard language. This was another language that explored data abstraction. Just as an aside, Alphard did not have a heap. It was not a heap-based language. And this meant that Bill and Mary had to worry about how much space to allocate for abstract objects on the stack. And this was a big deal, because when you want separate compilation, this means you don't necessarily know when you compile the user, what the UZ is like. And so then you have this whole issue about how do you allocate stuff on the stack, which we totally avoided because we were a heap-based language. So that simplified our design. Anyway, Bill and Mary told us about this idea they were working on called generators. And generators are roughly what Java has. So it's like an auxiliary type that you can use to iterate over the collection. It has an operation to get started, an operation to get the next element, and so forth. And we could see right away that this was a nice solution to the problem, except we thought it was kind of ugly. And so on the airplane flying home, Russ Atkinson, one of my students, invented iterators. And iterators are a form of generator that's much more elegant. That's a kind of a 95% solution. It doesn't have the same power that generators have, but we decided that it was better to have a simple mechanism that worked 95% of the time, and then you could always use generators for the rest. Okay, so here's an iterator. You can call it in a for loop. Here's the members element, members operation for sets. It's going to give you all the members of the set one after another. So you call it into the for loop. Whenever it has something to return, then you run the body of the for loop. After you run the body of the for loop, we go back in the iterator. It sort of picks up where it left off. And when finally it's produced everything, then it returns, and that terminates the for loop. So it's a very simple, straightforward thing. It does not have the power of generators. I, for example, cannot take two trees and run over their fringes side by side using iterators. I can use them nested, I can use them recursive, but I cannot run them in sort of a parallel structure. And here's a simple example of a very simple-minded iterator, but they were very nice for complicated iterations also. And the reason was that rather than having to store the state of the iterator in an object that I created, it just sat there on the stack as program variables, and when I returned, I just picked right up where I left off, sort of knowing exactly what I had done last time. One final point about iterators is we also had a very simple and efficient implementation for them. Basically, we packaged up the for loop body as a little procedure, passed it as an argument to the iterator. So then whenever the iterator yielded, it called the procedure. When the procedure returned, we continued in the iterator. When the iterator returned, you were all done. This is kind of like a very simple form of coroutine. Okay, so that was Clue. And this work went on, took me quite a number of years. I think that we had many variations on the versions of the language, Clue 0, Clue 0.5, Clue 1. And we used a kind of bootstrapping technique where we started off implementing a little compiler for Clue 0 in a language called Muddle, which was a Lisp derivative. And then once we got past that stage, then we kept writing the Clue compiler in Clue. And of course, a compiler is a pretty powerful program. You get a pretty good idea of expressive power just by using the language for the compiler itself. So I finished the work in Clue around the late 70s. And at that point, I had a choice. I could either go on and do new research, or I could think about commercializing Clue. And I chose to do research. I chose not to try and commercialize Clue. It was probably a really smart decision, but I've always wondered about the road not taken. The thing was, it wasn't that easy in those days. Today, you might put stuff off as freeware. People would start to pick it up. In fact, Clue was quite widely used for a while, but in those days, to really cut into the market, you had to be a company with a team of programmers and so forth. So I, in fact, moved into distributed computing, sort of like serendipity. So I looked around, and there was the ARPANET. And, in fact, I was already using email. And people were talking about, wouldn't it be wonderful if we could build distributed programs? Programs that ran, but they had no idea what this meant. And so I thought, aha, here's a really good problem. And so I went and did this Argus project, which was the first language that supported distributed programming. And Argus is an object-oriented language where the objects reside at different machines. They communicate by remote procedure calls. It had a bunch of other stuff in it as well. But it was just a very nice juxtaposition that happened at that time. And of course, it's got concurrency in it, because once you go into distributed systems, there's naturally many users of any particular object and so forth and so on. So I sort of picked up that concurrency that I put aside in Clue when I got to Argus. And I've mostly been working in distributed computing ever since, although I kept working on programming methodology for quite a long time, and I was very interested in how do you specify data abstractions, how do you reason about their correctness, how do you design. I developed a course at MIT, and one of the things I did in this course was I had the students implement 2 operations in addition to the ones that belong to the data type. One of them was what I called rep OK, which is basically checking the rep invariant. And so you could keep checking the rep invariant to see whether it was broken or satisfied whatever the constraints were. The other one was toString, which is basically the abstraction function and allows you to take any concrete object and give an abstract representation of it so you can look and see what it looks like. And I felt that was valuable because it gave the students a real understanding of what this type was all about. Okay, so I want to close by talking a little bit about type hierarchy. So what happened was that I was asked to give a keynote at UPSLA in the fall of 1987. And I decided that a good thing to do in preparation for this talk was to go into the world of object-oriented programming and see what had been going on there. So the work on Smalltalk was going on simultaneously with the work on Clue, but sort of completely separated. And I hadn't been paying very much attention. It seemed like a good chance to check in. And what I discovered in reading these papers was that there was quite a bit of confusion. And I think the confusion was due to the fact that people were using inheritance for 2 different reasons, but they hadn't actually sorted out that these reasons were different and that different mechanisms were needed for them. So if you think about Java today, there's a distinction made between inheritance as a way of implementation and inheritance as a way of expressing type hierarchy. And I wasn't personally all that interested in the implementation part of it, but I was very interested in the type hierarchy part. And I could see in these papers that type hierarchy was not well understood. So I remember reading a paper in which the author claimed that stacks and queues were each a subtype of one another. And I thought this really can't be true, because if I wrote a program that expected a stack and you gave me a queue, I'd probably be pretty confused at what was going on because I expected LIFO and I got FIFO, or vice versa. You know? So it seemed to me that people just hadn't quite figured out what they meant by this type hierarchy. And so what I did for that UPSLA paper was I came up with this thing that came to be called the Liskov substitution principle. And it's really just common sense, okay, if you think about it. I mean, what I said was objects of a subtype should behave like those of a supertype if used via supertype methods. You know, which is sort of exactly what you want. I write a program in terms of the supertype specification. I interact with the object using the supertype methods. I expect them to obey the supertype specification. I don't care what happens with the other operations because I'm not using them, but I care about the operations I expect. So I think it was really just common sense, but nobody had said it before. And it came to be called the Liskov substitution principle, so I would never have, you know, so here is the Liskov substitution principle. But what happened sometime in the 90s was I one day got an email from somebody saying, can you explain to me whether this is the proper interpretation of the Liskov substitution principle? And then I discovered there were chat groups and they were arguing about it and so forth, and so it was really pretty funny. Okay, so I'm pretty much done. What next? Okay, so here's the astounding thing that I discovered when I got the Turing Award. I hadn't been thinking about this. Those ideas that were developed by myself and others during the 70s and early 80s, they are the way we think of building programs now. And I just hadn't been thinking about it at all. In fact, when I got the Turing Award, my husband was online all the time, looking at, you know, the new things that were happening, because there was a lot of press and lots of comments and so forth. And one day he came across this quote from somebody saying, what did she get the award for? Everybody knew this anyway. And I thought, you know, that was really amazing validation, actually, because the truth was everybody didn't know it. But now it's just the way we do it. So that is really remarkable. I mean, we live in we're working in an amazing field. Things have changed so much. You know, we're affecting the whole world. It really is quite amazing. Okay, but you know, not to worry. There's lots to do. Computer science is actually at a very exciting time. If you think about what's happened in the last 10 years with the development of the web and the way that the web has infiltrated people's lives so that it's just changing the way the society lives, I mean, this is amazing. And inside here are marvelous technical challenges. And then, of course, Computer science is moving into all sorts of scientific disciplines. You know, computational biology is big right now, but you can see that there's going to be others. And so it's another very exciting thing. So we live in a very exciting time. What I have on this slide are challenges in the systems area, because I have sort of stayed firmly in the systems camp. And I haven't worked on programming languages after Clue and Argus, because I felt if I was going to do it again, I'd want to have another mechanism like data abstraction that made such a difference. And I didn't have such an idea. I hope that somebody comes up with such an idea, because what happened was data abstraction raises the level of discourse so that you can write bigger programs with the same amount of intellectual effort that you had to spend, before on something smaller. And if we could get another abstraction mechanism, we could do it again, and that would be really valuable. But I have no ideas about what that would do. However, maybe this will come out of work on massively parallel computers, which I view as being one of the key challenges of our time. Now, God did not say that we have to have multi-core machines. And that, just because Moore's law is running out, this does not mean that we have to consume computers with hundreds or thousands of processors in it. It's possible we will never be able to do it. It's possible that there will be embarrassingly parallel programs that run on those machines, but other programs won't really be able to take advantage of all that parallelism. This could happen, but we don't know. We don't know how to program those machines for programs where there is interaction among the parallel pieces. So that is the real challenge of our time for this area. Can we write those programs? And my view is you have to start by understanding how to write those programs. And we don't really understand that very well. And then if somebody has a bright idea about how to write those programs, then the programming language will follow, people will learn how to do it, and we'll really make progress in that area. There is MapReduce. That's a good step. But only certain problems fit into the MapReduce paradigm, and there are a lot of others that don't fit so well. So that's a really important challenge. And then I'm very interested in the internet as a computer. And I have here, the things I think are interesting. You talk about the cloud all the time. If you look at what's going on in the cloud, what you see is the semantics is not that great. So storage, it's not secure. The semantics isn't very well defined. It's not very reliable. It's not very available. This is not so great. If I'm going to entrust my precious data to the cloud, I would like to know that it'll be there when I get back and that it hasn't been stolen and so forth. And similarly for computation, if I'm going to be running computations on one of those cloud machines, I'd like to know that my private data is not being stolen by the computation next door and so forth. So I think there's huge challenges in the systems area as well. And that's the end. So I'd be happy to answer questions if anybody has them. Yes?
When you were thinking about clusters, did you ever think about the evolution of clusters, notably the removal operations from data types, and what that would do to consumers of those data types?
So the removal of operations? So we did define a notion of completeness. And so one of the requirements for a cluster or an abstract data type is that it have a sufficient number of operations that you can do everything you have to do with those operations. And as a general design methodology, you need completeness, and then you might add a few extra operations just to make things a little more convenient, where I might have had to call two operations and I can get one that combines them. I certainly have not thought about taking things away. So, what were you having in mind for that? Did you have an idea of what you meant by taking away?
Large, well-used libraries such as in Java, obviously you want to add to interfaces, for example, add operations, and you ultimately want to remove sometimes. And there are ways to handle the additions, but handling removals, you can sort of come up with these pseudosciences you can deprecate and denigrate.
Okay. So I have done some work on software upgrades, all right, and adding operations is fine, provided what you end up with is a subtype of where you started. If it's not, in fact, you have to deprecate. So the truth is what you're talking about is I have a certain kind of behavior. If I need to change that behavior in a way that's compatible, no problem. If I have to change that behavior in a way that's incompatible, problem. And then, there's no, so I actually wrote a paper with one of my students about a sort of a gradual evolution. So the idea was that For a while, you would simulate the old type using the new one with some extra stuff. But eventually you get to the point where you say, I'm tired of doing this. Sorry, users, you know, July 5th, that's the end of this old stuff. You have to switch to the new stuff. But there is definitely a methodology that allows you to run a system with both implementations in place. So users of the old interface can still get the behavior they want at the same time that the new one is there, giving the users a time to sort of move to the new interface. Okay. Yeah.
Barbara, I was reading something, commentary this guy had about flight control software, where he's making the point that he didn't think we should ever use object-oriented programming with flight control software. And I thought he was a bit of a Neanderthal, but I think I can summarize his point as the correctness assumes the Liskov substitution principle that languages don't ensure that. Have you encountered any work which has tried to ensure this substitution principle is followed?
So the substitution principle is a semantic principle, right? So it says that the subtype has to behave like the supertype. And the best a language can do is to guarantee that it has compatible operation signatures, right? So he's absolutely right. I mean, you know, I'm not sure he's right in saying it shouldn't be there, but he's absolutely right that the methodology is not enforceable by sort of normal compilers. We've walked into a program verification domain here. Now, program verification has become more and more powerful, and it might be that this is something that could be, you know, tackled, where you start to actually try to prove, because we're talking about proving, you try to prove that this type is a subtype of that type. But I don't think you throw out object-oriented programming on these grounds. I mean, I encountered a program, once I was hired as an expert witness, and I was given this huge object-oriented program to try and make sense of. And it was horrible, you know. I mean, there were classes, there were subclasses. You never knew when you encountered a variable. It was of type T in theory, but, you know, you didn't know where it came from. In fact, I'm talking about exactly the same thing he talked about. If I'd known Liskov substitution principle was there, then I could have reasoned about it from the point of view its declared type, but I couldn't do that because I had to keep reminding myself of what type it really was. And so it makes it very hard to understand. And it's a bit akin to what I said about changing the syntax. If you think about it, you know, I've got this program text, I see a symbol there, and it says one thing, but I don't know if it really means that. So I would sort of turn it around. I would say that to the extent that we can figure out ways to actually prove these properties, it will greatly enhance our ability to think about the programs. Yeah.
Or when we do concurrent computation or parallel computation, we tend to make the programming languages and the concepts up out of serial computation primitives. And do you think that's the right approach?
Maybe not. But I really believe that first we have to come up with the schemes. And maybe, I mean, I've heard people say things that I think are ridiculous. They sort of imagine the compiler can solve the problem. You know, you write a sequential program, the compiler will develop this massively parallel. Now, you know, maybe this will in fact be true someday, because maybe we will come to the point where we will understand sort of a way of going from a sequential program to a parallel program. But first we have to understand that way. And it may very well be that that way is to think more concurrently than we're accustomed to today. But I just think this is a huge challenge. Yeah.
On that point, the problem is that the language colors the algorithms the programmer chooses. And a sequential language, the programmer will choose sequential algorithms that are hard to parallelize.
Yeah. But I do think it's really important to put the methodology first and the language second. Now, you know, the people who go first, they have to make a transition. So they may have to deal with a sequential language and think in a different way. But then after that, if you can make that step, then we can take the next.
Language structures, they'll have to encourage parallel thinking.
Yes.
So the compiler will have a prayer.
Yeah. Yes, and I think you also remember the days of the connection machine and the data parallel machine. You know, that was a nice concurrent structure for the programs that it worked on.
But Alan, your colleague Ken Iverson said it's all in APL.
And APL will encourage parallel thinking.
Yes.
I have a lovely use case from a guy from CERN, where he claimed that the particle tracking algorithms were not vectorizable. And I taught him APL, and it turned out they were 100% parallelizable once he started thinking APL.
That's good. So I just think this is going to be a really interesting research area, and I hope somebody comes up with some great ideas. Okay, I guess.
Thanks a lot.
Yeah.
For more, please visit us at stanford.edu.